As you might know, the plasma membrane is a hydrophobic barrier that separates two aqueous mediums, the cytoplasm of the cell and the extracellular matrix. As such, the membrane prevents any hydrophilic substance or, in other words, any water-loving substance, from entering or exiting the cell. One such hydrophilic substance is ions. When dealing with neurons, the most relevant ions we will encounter are calcium, potassium, chloride, and sodium, which all bear their respective charge. Due to the polar nature of water, ions attract water molecules. Indeed, even though water molecules have a neutral charge, the high electronegativity of oxygen creates a net dipole moment that partially shifts the electrons towards the oxygen. This thus creates a partial negative and partial positive charge on the molecule. These partial charges interact with ions in a complementary way, the partial positive with the negative charge and vice versa. In solution, these interactions envelop ions in what we call hydration shells, and these shells are exactly what prevents the ions from crossing the membrane. To cross the membrane, ions go through particular proteins that are embedded in the membrane. Many different classes of these proteins exist, but for our discussion today, we will cover ion transporters and ion channels. When ions flow through ion channels, their motion does not require any energy expenditure because the ions follow their electrochemical gradient, which is a property I will explain shortly. For this reason, movement through these channels is said to be passive. On the other hand, ion transporters move ions against their electrochemical gradient, and this process requires energy, usually in the form of ATP, which makes this an active transporting mechanism. As I've mentioned in the overview, there is an imbalance of ions across the membrane, which results in an imbalance in electric charge. To see where this imbalance comes from, let me first explain what is the electrochemical gradient for an ion. So, regardless of their charge, ions are subjected to two main forces that dictate their movement. The first force being the chemical gradient, and the second being the electric gradient. To see how these forces influence ions, imagine two different scenarios. In the first, there are two equally concentrated solutions of potassium chloride that are separated by a membrane only permeable to potassium. In the second scenario, imagine that the solution on the left-hand side has double the potassium chloride concentration with respect to the right side. Here again, the two solutions are separated by a membrane only permeable to potassium. Obviously, in a physiological depiction, the ions will be disorganized and moving randomly, but for the sake of making it more visually clear, I will group the ions linearly as shown here. Now, what you have to imagine is that the movement of ions is always dictated by how they can equilibrate the system. In terms of the chemical gradient, this means that the ions will always move from a region of high concentration to a region of low concentration in order to balance the amounts on each side. For the electric gradient, this means that ions will always naturally move to the opposing charge in comparison to their own, such that the net charge of the system is as close as possible to neutral or zero. In some way, we can say that for ions, their ideal situation is to be equally as concentrated on either side and also to be electrically neutral as a system. This ideal situation is exactly what is depicted in the first scenario, where there is no imbalance in either charge or concentration, so even though the potassium ions can cross the membrane, there is no net change in charge or concentration. In the second scenario, however, since there are 2 times more potassium chloride on the left side, the chemical gradient will drive the potassium to equilibrate by crossing over to the right. Remember that here, it's only the potassium that crosses because it is the only ion that the membrane is permeable to. By doing so, you will notice that even though now the potassium is equally concentrated on either side, the departure of potassium has left behind many negatively charged chloride ions. This creates a net positive charge on the right and a net negative charge on the left. Since potassium is positively charged, it will be drawn to the left side because it is attracted to the net negative charge created by the free chlorides. In the second scenario, you can see that both the chemical and electrical gradient influence the motion of potassium, and it occurs mainly because there is an uneven distribution in initial concentrations. If potassium continuously flows, At some point it will equilibrate such that the force it feels from its chemical gradient is equal to the force it feels from the electric gradient. As you can see in this example, regardless of how the potassium ions move, it won't be possible for them to be equally concentrated on either side and fully neutralize the charge. Nonetheless, their drive to equilibrate the chemical and electrical gradients is equally as strong, which essentially constitutes a form of equilibrium for potassium. As a result of the difference in charges between the inside and the outside of the cell, we can establish the membrane potential, which corresponds to the voltage across the membrane, or in other words, the difference in voltage between the extracellular matrix and the cytoplasm. In our example here with potassium, we can also establish its equilibrium potential, which is the membrane potential at which the drives from the chemical and the electrical gradients are equal for the ion. The equilibrium potential for any ion can be mathematically computed with the Nernst equation. In this equation, the equilibrium potential for an ion is equal to the gas constant multiplied by the temperature in Kelvin divided by the valence of the electron, which is essentially its charge, multiplied by the Faraday constant, and all of this multiplied by the natural logarithm of the outside concentration of the ion divided by its inside concentration. When certain conditions are assumed, for example 37 degrees Celsius, the equation can be simplified to 26.72 millivolts times the natural log of the concentration over the valence. We can further simplify the equation by converting the natural log to a base 10 log by multiplying by about 2.3. The conversion will make the calculations a bit more convenient and more intuitive later on. In all, this leaves us with this equation, which we can now use to compute the equilibrium potential at 37 degrees Celsius for each ion that contributes to the membrane potential. To do so, we need the concentrations in and out of the cell for each ion and their valence. With data taken from this textbook, we can compute the equilibrium potential for each ion. You will notice that, let's say for sodium, the concentration inside varies from 5 to 15. Hence, the equilibrium potential also varies. You will also notice that I have added anions to the table. In this case, anions are negatively charged amino acids and proteins that influence the net charge of the system, or in other words, the membrane potential, but since they cannot move directly through the membrane, we will not consider their equilibrium potential. As you can see from the equilibrium potential column, the values greatly change depending on the ion. Sodium, for example, would be perfectly at equilibrium if the membrane potential was between positive 89 and 60 millivolts, whereas potassium would be at electrochemical equilibrium if the membrane potential is at negative 88 millivolts. As we will see time and time again in this video, this contrast in equilibrium potential between potassium and sodium is exactly what fuels the propagation of the signal. Now, an important detail we have not discussed yet is how exactly do the ions end up distributed the way they are, and most importantly, how is this distribution maintained across the membrane? Thank you for watching this video. If there was anything unclear or there was a mistake somewhere in the video, make sure to let me know in the comment section. If you enjoyed this video and found it useful, you can consider leaving a like and subscribing to support the channel. On the right, you will see the informational resources that I've used to produce this video. Thank you again for watching, and I'll see you in our next discussion.